Imagine a place where gravity reigns supreme, a place where the very fabric of space and time is twisted and contorted. Welcome to the enigmatic world of black holes, a place so dense that nothing, not even light, can escape its pull. This is the realm of black holes, one of the most mysterious and fascinating phenomena in the universe. But what exactly are black holes, and how do they form? Black holes are cosmic abysses that have captured the imagination of scientists and stargazers for decades. They are regions of space-time where gravity is so strong that it warps the fabric of the universe itself. Imagine a trampoline with a heavy ball in the center, distorting the surface around it. The concept of a black hole challenges our understanding of physics and the nature of reality. They are formed when massive stars collapse at the end of their lives, leaving behind an incredibly dense remnant. This process is akin to a colossal implosion, where the core of the star is crushed under its own gravity. This collapse is so powerful that it compresses the star's core to a point of infinite density, known as a singularity. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape. Think of it as the ultimate point of no return. The event horizon is not a physical surface but a point of no return. Once something crosses this boundary, it is forever lost to the black hole's immense gravitational pull. Even light, the fastest thing in the universe, cannot escape once it passes this threshold. This means that not even light, the fastest thing in the universe, can escape once it passes the event horizon. This is why black holes are invisible to telescopes that detect light, X-rays, or other forms of electromagnetic radiation. So, how do we know they exist? However, we can infer their presence by observing their effects on nearby stars and gas. For instance, we can see stars orbiting an invisible object or gas being pulled towards an unseen force. These cosmic dances provide crucial clues. These observations provide indirect evidence of black holes, allowing us to study these enigmatic objects despite their invisibility. It's like detecting a ghost by the way it moves objects around it. The study of black holes not only helps us understand the life cycles of stars but also offers insights into the fundamental laws of physics. They are laboratories for testing theories of gravity, quantum mechanics, and the nature of space-time. Imagine the possibilities of what we could learn. As we continue to explore the universe, black holes remain one of the most intriguing and challenging subjects in astrophysics, pushing the boundaries of our knowledge and imagination. They are the ultimate cosmic enigmas, waiting to be unraveled. The existence of black holes raises a profound question. Can something so powerful be destroyed? The very notion seems impossible. After all, how can you destroy something that devours everything in its path? Yet the laws of physics suggest that even black holes are not invincible. Scientists have proposed several theories about how black holes might meet their demise. One such theory involves Hawking radiation, a process where black holes could slowly lose mass and energy over time. This radiation, predicted by Stephen Hawking, suggests that black holes could eventually evaporate completely. Another theory involves the collision of black holes, where the resulting gravitational waves could potentially lead to their destruction. These theories are highly speculative, but they offer a glimpse into the extreme physics that govern these cosmic behemoths. Exploring these possibilities takes us to the cutting edge of our understanding of the universe. To understand how black holes might be destroyed, we must first understand what they are. Black holes are one of the most fascinating and mysterious objects in the universe. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. This makes them invisible to the naked eye, and they can only be detected through their interaction with other matter and the effects of their immense gravity. Imagine a bowling ball placed on a trampoline. The bowling ball creates a dip in the fabric of the trampoline, much like a star creates a dip in the fabric of space-time. This analogy helps us visualize how massive objects like stars and planets warp the space around them. The trampoline represents the fabric of space-time, and the bowling ball represents a massive object. The more massive the object, the deeper the dip it creates in the trampoline. The more massive the object, the deeper the dip it creates. A black hole, however, is like an infinitely heavy bowling ball. It creates a dip so deep that nothing can escape. This is because the gravitational pull at the event horizon, the boundary around a black hole, is so strong that it pulls everything, including light, into the black hole. The event horizon is the point of no return, beyond which the gravitational pull becomes inescapable. Black holes are not really holes in space, but rather regions of extremely warped spacetime. They are formed when massive stars, much more massive than our Sun, run out of fuel and collapse under their own gravity. This collapse compresses the star's core to an incredibly small and dense point called a singularity. The singularity is a point where the density becomes infinite, and the known laws of physics can no longer describe the conditions. The singularity is the heart of a black hole, a point of infinite density where the laws of physics as we know them break down. The event horizon is the boundary surrounding the singularity, beyond which nothing can return. The immense gravity of a black hole can even bend light, causing a phenomenon known as gravitational lensing. This bending of light allows astronomers to detect black holes indirectly by observing the light from stars and galaxies that pass near them. Black holes can vary in size. Some are only a few times more massive than our Sun, while others, known as supermassive black holes, can be millions or even billions of times more massive. These supermassive black holes are often found at the centers of galaxies, including our own Milky Way. The formation of supermassive black holes is still a topic of research, but they are believed to play a crucial role in the formation and evolution of galaxies. The process of a star collapsing into a black hole is a violent and energetic event. When a massive star exhausts its nuclear fuel, it can no longer support itself against the force of gravity. The core collapses, and the outer layers are expelled in a supernova explosion. What remains is a black hole, a region of space where the gravitational pull is so strong that not even light can escape. This collapse happens in a fraction of a second, releasing an enormous amount of energy. Understanding black holes is crucial for understanding the universe. They play a key role in the formation and evolution of galaxies, and studying them can provide insights into the fundamental laws of physics. Despite their mysterious nature, black holes are a testament to the incredible power of gravity and the fascinating complexity of the cosmos. The study of black holes also helps us understand the behavior of matter under extreme conditions, which can have implications for other areas of physics. The singularity is the heart of a black hole, a point of infinite density where the laws of physics as we know them break down. It is a place where our current understanding of the universe ceases to apply, and it remains one of the greatest mysteries in astrophysics. As we continue to study black holes, we hope to unlock more secrets of the universe and gain a deeper understanding of the forces that shape our cosmos. The study of singularities could potentially lead to new physics that goes beyond our current theories. In the 1970s, physicist Stephen Hawking proposed a revolutionary idea: black holes are not entirely black. This groundbreaking concept challenged the prevailing understanding of these enigmatic cosmic entities. Before Hawking's proposition, black holes were thought to be regions of space where gravity was so strong that nothing, not even light, could escape from them. He suggested that they actually emit a faint radiation, now known as Hawking radiation. This radical departure from the traditional view opened up new avenues of thought in theoretical physics. The idea that black holes could emit radiation was both fascinating and perplexing, implying that black holes were not the eternal prisons of matter and energy that they were once thought to be. This radiation arises from quantum effects near the event horizon, the boundary beyond which nothing can escape. The event horizon is a critical region where the gravitational pull of the black hole is so intense that it warps space and time. Quantum mechanics, which governs the behavior of particles at the smallest scales, predicts that particle-antiparticle pairs can spontaneously form near the event horizon. One of these particles can fall into the black hole while the other escapes, resulting in the emission of radiation. Hawking radiation is thought to be incredibly weak, far too faint to be detected with current technology. Despite its weakness, the existence of Hawking radiation has profound implications for our understanding of black holes and the nature of the universe. It suggests that black holes are not completely isolated from the rest of the cosmos, and that they can interact with their surroundings in subtle ways. However, over vast stretches of time, Hawking radiation could cause a black hole to slowly lose mass and eventually evaporate entirely. This process is incredibly slow, taking place over timescales that are almost incomprehensible to the human mind. As the black hole loses mass, it would shrink in size, and the rate of radiation emission would increase, leading to a gradual but inevitable demise. The timescale for black hole evaporation through Hawking radiation is incredibly long, far longer than the current age of the universe. To put this into perspective, the universe is approximately 13.8 billion years old, but the time required for a black hole to evaporate completely through Hawking radiation could be many orders of magnitude greater. For a typical black hole, the evaporation time would be many orders of magnitude greater than the current age of the universe. This means that while the concept of black hole evaporation is theoretically sound, it remains a distant and almost abstract possibility in the context of our current understanding of cosmic timescales. But the fact that it could happen at all challenges our understanding of these cosmic objects. It forces us to reconsider the nature of black holes and their role in the universe. The idea that black holes can emit radiation and eventually evaporate adds a new layer of complexity to our understanding of these mysterious objects, and highlights the intricate interplay between gravity and quantum mechanics. Another way black holes could theoretically be annihilated is through a cataclysmic collision with another black hole. When black holes collide, they merge in a titanic event that sends violent ripples through space-time, known as gravitational waves. These waves carry away immense energy, and in the process, some of the black hole's mass is converted into pure, raw energy. These collisions are among the most explosive and energetic events in the universe. They offer scientists a rare and invaluable opportunity to study the very fabric of gravity and the behavior of matter under the most extreme conditions. While these collisions don't obliterate black holes in the traditional sense, they dramatically alter their properties and unleash vast amounts of energy into the cosmos. Some scientists have ventured into the realm of the unknown, speculating that a sufficiently powerful explosion, perhaps involving exotic forms of matter or energy, could potentially obliterate a black hole. Yet the energy required for such a cataclysmic event would be astronomical, far beyond anything we can currently fathom. Another tantalizing possibility is the existence of white holes, enigmatic objects that are the theoretical opposites of black holes. While black holes voraciously consume matter and energy, white holes would mysteriously expel them. Some theories whisper of a cosmic connection, suggesting that a black hole and a white hole could be linked, forming a tunnel through the very fabric of space-time. The existence of white holes remains shrouded in mystery, a topic of endless debate and speculation among scientists. If a black hole were to be destroyed, the consequences would reverberate across the universe, shaking the very foundations of existence. The release of energy from such an event would be colossal, unleashing powerful gravitational waves that could warp the fabric of space-time itself. These waves could send planets and stars spiraling out of their orbits, causing chaos even in the farthest reaches of the cosmos. The obliteration of a black hole could also unleash a storm of particles and radiation, some of which could be devastating to life. Yet the likelihood of such a cataclysmic event occurring near Earth remains exceedingly low. Black holes remain one of the most enigmatic and fascinating objects in the universe. They represent the limits of our current understanding of physics, and their study continues to challenge our assumptions about the nature of gravity, space, and time. While the question of whether we can destroy a black hole remains open, the pursuit of an answer leads us on a journey into the deepest mysteries of the cosmos. As we continue to explore the universe, we can expect to uncover even more surprises and challenges to our understanding of the cosmos. The universe is full of wonders, and black holes are just one of the many mysteries that await our exploration.